and General Manager of the Machine Learning group within the software uh, group, software group. Wei Li and I go a long way together. We met in the 90s when Wei joined Intel after completing his, no, actually you worked before also, but he got his PhD from Cornell University and then joined Intel during the 90s. Wei Li's his thesis and most of his years at Intel worked on compiler technologies, including binary translation and other optimization technologies. And lately moved, like many of us, to work on machine learning related technologies. And he's going to tell us what Intel and his team and organization are doing in this field. So thank you for coming.
Thank you, Shalom. As Shalom said, when I joined Intel, I actually sat next to him. So at that time in the 90s, Intel was growing before the bubble burst, right? Intel was growing, and we had all these compressed cubicles. And each cubicle, you know, even today's cube is not that big. At that time, it was even smaller. So we only have a table and a chair, and he was the one next to me. So got a chance to know him for quite a few years before he moved back to Israel. So I come to Haifa very often, at least once or twice a year. Nowadays, more once a year, and I've been coming for more than 10 years at least, 10 to 20, 10 to 15 years. You know, I always wanted to have a chance to come to Technion because it's such a well-known university, and I never got a chance to do it. So I'm very glad to be here today and to give you a chance to tell you what's going on what we're doing here. Before I boarded my flight from San Francisco, I actually live in Palo Alto, which is chatting with one of your professors here. So I actually met with the dean of computer science from Cornell, because I graduated from Cornell, which is still kept in touch. I was talking to him about, you know, this joint Cornell Technion thing going on in New York City, right? So I don't know how much you guys are involved in collaborating with them. So he seems very happy. The two groups are working very well together in New York City. Sometimes they cannot even tell who is from Cornell, who is from Technion. So I was telling him, you know, I finally got a chance to come to Technion today. So I'm very glad to be here. What I want to tell you here is what we're doing on machine learning. And when I showed the title to people before, and one person said, are you sure you have the right title? Do you have a typo here or not? Is it really CPU or something else, right? Okay, so what I'm hoping to do is to convince you this is not a typo. It is real. It is actually what I do want to tell you about machine learning, particularly deep learning on CPU. Now, there's a lot of applications on AI. The fact, you know, all of you guys take your time to come to this talk is you're convinced AI is going to do something finally for all of us, right? So when I was in grad school, like many of you guys, AI was not that hot actually. We stayed away from AI. We all wanted to do something else. I actually did my PhD in compilers for supercomputer. At that time, supercomputer was a big deal, at least in the US. There was a lot of research going on. So now AI seems to be real. Now, a few years ago, I had a team working on mobile devices. At that time, mobile was very hot. So we actually had to test these mobile devices. As you know, a lot of these mobile applications tend to be interactive, right? The mobile gaming, you know, games people are playing. So the way to test it is not very straightforward. You cannot really just automate test the thing. So we actually had to originally hire a bunch of testers to do this. Now, initially, it was an interesting job because when I mentioned to my son, who was in middle school at that time, I said, I'm paying people to play games. And he said, can I get that job, right? Yeah, I want to get paid and play games. But on the other hand, this is not really a very exciting job if it becomes a job. So we actually, hired somebody, and on the same day, the guy just quit because they couldn't handle this boring, tedious job of playing the same game again and again every day here, right? So we actually, our team came up with a robot, sort of robot, to test this automatic using machine learning. We actually use a deep learning for this. Unfortunately, when we try to train our model, so the model worked out very nicely. We can actually find more tests, more bugs than humans can find out. So the machine actually does a very good job. The only thing is when they train the model, we cannot use the machine in our lab to do this. So they end up, buying a GPU for this. So I have to find a budget to say, hey, this is, whatever thousands of dollars we have to pay to buy a extra GPU for this, because the CPU was not really set up to do deep learning at that time. That was about 3 years ago. Now things have changed in the past 3 years. As part of my job, I had a chance to go out, talk to a lot of people, including a lot of customers. And quite often, I talk to, for example, a big hotel chain in India. They tell me they have a lot of data, they just don't know what to do with it, right? And I talked to a big automotive company in US. They tell me the same thing. They have a lot of data. So the amount of data is growing very significantly, but the amount of data used for analytics or AI is very limited. So we have a lot of potential here. Now, part of this deep learning revolution is we have a lot of compute capability to make deep learning work. Not only data, but also a lot of compute. The algorithms have changed over time in the past few years as well. So when deep learning started about 5 years ago, at that time, we have mainly in the image processing field, people became very successful for recognizing digits, for recognizing faces, and so on, using CNN. And over time, we have evolved from CNN type of algorithms to RNN to something like recommendation systems to something like reinforcement learning. So there's a variety of things going on right now. And part of the job here is how to figure out a way using hardware or software to run all of these things efficiently. And there's a lot of activities doing accelerators, right? Wherever I go to these conferences, NIPS or wherever, you can always run into people who want to raise money. They may have raised some money already. They're doing another accelerator for deep learning, right? But the challenge here is how general purpose you can make it. Because if you're soon too narrow, you may only work for a particular thing. You won't work for other things anymore. So Intel's strategy right now. Intel's strategy right now is actually to do both. So we are actually in a very unique position where we have very successful CPU business, particularly on the server side. We have Xeon, where Xeon is everywhere, right? Whenever you have a data center, you have a lot of Xeons in it. Whenever you have a cloud, you have a lot of Xeons in it. So the Xeon really is everywhere. So it's so easy for people to find and just run something on top of this. And Intel continue to improve Xeon by adding new features on machine learning. For example, the most recent thing we're adding is called DL Boost. It's a new instruction. Actually, Renat from my team, they worked on these instructions, and they're the ones who actually proposed these new instructions here. And Intel is also investing in accelerators, what we call discrete AI. And within that particular bracket, we have both accelerators for inference as well as accelerators for training. Okay? Now, today's talk is mainly on the CPU side, and I won't touch on the accelerator side that Intel is doing. So on the CPU side, when you go back, as I mentioned earlier, my PhD thesis was on supercomputers. So at that time, in the 90s, when you have a 143 gigaflops, that was the fastest supercomputer in the world, right? And then a few years later, another fastest one, was only 1 teraflops. It was a big deal to break the 1 teraflop barrier here. And these computers were all only available inside national labs. It's not like anybody can can have their hands on these supercomputers. Now, fast forward to just last year or 2 years ago now, in 2017, when Intel launched our server called Skylake. By the way, it was designed in Haifa here. That alone, one single system has 8 teraflops inside already. So a single server has a lot of these supercomputers from 20 years ago. Now, as I mentioned earlier, Xeon is also everywhere, inside data centers, inside cloud. So when you have a data center with hundreds or thousands of these Xeons in it, the amount of flops you have is actually very meaningful. You do have a lot of flops inside where you can leverage here. Now, a key part of deep learning is going to be software, right? So you have these base capabilities in terms of compute, and how do you train these models? How do you use these models? And usually you go through these popular frameworks, right? You go from TensorFlow from Google, Caffe from UC Berkeley, PyTorch from Facebook, for example. So there are a handful, probably less than a handful of these popular frameworks everybody's using. And it plays a key difference in terms of performance. So as I mentioned to you earlier, about 3 years ago when my team tried to use a CPU to do deep learning work, it was not working primarily because the software was really not optimized. Because when people design these frameworks, they did not spend the time to tune performance on CPU. Okay? So let me tell you how things have changed in the past few years. So right before the holidays, Intel had an event called Intel Architecture Day, where we show the Intel strategy on our hardware roadmaps and the hardware strategy as well as the software strategy over there to a group of technical press. Okay? So in that event, I actually did a demo. My team came up with a demo. I happened to be the lucky one to show the demo to the press over there. So what we did was we compared performance on Intel CPU for the past few years. And we have the Skylake, which was launched in 2017. We show the old software before optimization as the baseline. And then we show the optimized software that my team did on Skylake at the time of launch, which is in 2017. And the difference was 50x. Okay? So it's a very meaningful 50x difference over there. Then we continued optimizing software. So on the same platform, Skylake, since Skylake launch to sometime today, you get another 5.5x. So software optimization alone on the same platform, Skylake, you got something like 275x performance gain out of this, right? And then you continue to add features in hardware. So our next generation hardware is something called Cascade Lake, which has a DL boost feature I mentioned to you earlier on this. And with the DL boost feature, you get another 2x. So really, people notice, like Forbes, they wrote an article on this. People notice we actually have orders of magnitude of performance added to CPU here. So because of the change we have made in the past few years, the market is responding to what we have done. So Intel in 2018 has been working with a lot of different companies, and many companies actually adopted CPU as a way of doing deep learning. And these are all sort of not unknown names around the world here. And when so our finance department actually looked into whatever we do, we want to show there's a business impact. After all, we are actually from a company. We're not from academia, right? So we need to show where the money is, and they came up with the estimate of more than $1 billion from the AI side alone. Okay, so how we do this thing here? How do we do make such a big progress on the CPU side? As you know, on the deep learning side, there are two phases. There's a inference side, there's also training side. You usually do training to develop your model, and then you do inference to use your model here. So for the rest of the presentation, what I want to show you here is on the inference side, how we did it, and I want to show you on the training side, how we did it, okay? Earlier last year, Stanford, I actually happen to live very close to Stanford, so they had a deep learning competition called the Down Bench. And we participated together with a whole bunch of other companies and so on. So Xeon actually won the inference side. So we are able to do inference very quickly. So for example, like the ImageNet ResNet 50 kind of model, we can do inference in milliseconds, right? In a single digit milliseconds. So that, that usually is meeting the criteria of our customers. So quite often our customer will come and tell us, say, we need 7 milliseconds. If you can get down to below 7 milliseconds, we're all very happy, right? So we're able to meet the customer requirements just by simply running inference on the Xeon side. You have a question?
Yeah, quick one. When you normalize the power consumption, you also improve or you do worse than?
So in this particular competition, they did not normalize against power. But if I tell you an estimate, we are on the power side, Xeon is sort of comparable to other GPU, and also, so if we win on the latency side, we win on the power latency also. We also win on the price side as well. So there's a few cents for 10,000 images and all that. So that was a little bit surprise to people actually. People tend to think CPU is just out of the game for deep learning, and they were surprised we actually, we're one of the three. I mean, the CPU, GPU, TPU, we all came out to be competitive in different ways, right? Now, what does that mean in the real business side? So Facebook actually has published quite a few papers to see what they actually do inside the environment. And one of the things they showed was, deep learning inference has been increasing very significantly, right? So you go from, in the 3-year period, they increase very, very significantly in terms of the kind of workloads they're running here. And then they also listed what kind of workloads they're doing inside Facebook. And the number one thing is actually news feed. So within news, so this 1x is just relative capacity, right? This shows this is really the most cycle-consuming workload they have, which is news feed. And then they have other workloads they're running here: speech recognition, image recognition, and so on. The news feed itself is basically a recommendation system inside. So you want to rank the kind of things you may want, and they want to sell your ads, and they want to feed your news and all that. So this is some way of ranking things. It's actually very popular among the big CSPs. So when I go to different big CSPs around the world, quite often actually, the number one workload they're running is a ranking recommendation system they're doing there. Okay. All right. So let's look at, dig a little bit deeper on this to see the kinds of workloads people are doing and how we do this thing inside on the CPU here. Okay? As I mentioned a little bit earlier, so when deep learning started, the most successful thing originally was CNN. It's convolutional neural networks, right? And so this is one example of CNN, which is ResNet 50, and it's being very widely used. And whenever you compare systems and so on, nowadays this has become like the spec, so the standard thing people at least have to demonstrate how well you do on ResNet 50. Okay, and it has, as the name indicates, has 50 layers, and these are most of these are convolutional operations here. Okay, So when you look at the overall compute, you want to analyze data here to see how does this workload look like from the performance perspective, right? And what our team found out was, you actually, majority of these are convolution, well, there's a conv operation, which is not a surprise, but majority of these are conv 1 by 1 is more than half, and conv 3 by 3 is more, it's a little less than half. That between these two, you are really more than 80, possibly 90% of the compute here. So if you do well on these, you probably can do well on the overall inference here. So let's look at a little bit more on the data here. So this shows when you have different tensor operations. So within the neural network, you think about these really multiple tensor operations, a lot of tensors going floating through, and these tensors have different shapes and so on. And then one of the parameters you do is you want to look at the batch size, because this statistically is a mini-batch deep learning, mini-batch level deep learning here, right? So the mini-batch size also has an impact in terms of how big the data is and so on. So if you look at these different data tensor types and the operations on top of this, so this gives you some idea about how often these different operations are being used inside this particular topology here. Now, when we look at further, so one of the key reasons we do well or not do well in terms of performance is when you look at the amount of data and you look at amount of compute on top of the data to see what the ratio is, right? This is what we call, this is what we're looking at, the ops versus data access for ResNet 50 here. Okay? And if you look at ResNet 50 here, so this shows, oops. So this shows the number of data access you have in that tensor operation. So most of these accesses tend to be in somewhere around 1,000 to a few thousand data accesses for each tensor operation here. And then within the tensor, for each data access, how many for each tensor, how many operations you have on top of this, and these operations tend to be somewhere between. So this is 10,000 over 1,000, so it's 10 operations per data access, okay? And we have this band of somewhere between 10 to 1,000. So when you look at, so this shows for something like ResNet 50, the number of operations per access is very significant, okay? So at least 10, somewhere, sometimes almost to 1,000 here. So that's the good news. That just means when you do data access, you have a lot of operations performed on the same data for these data accesses here. So how do you do this thing on a CPU? Okay, because it's very much compute bound. So what we do is inside the CPU, we have been historically investing in a lot of vector operations, right? In the old days, we have the MMX for media processing. And then we have the floating point vector operations and so on. So Intel invested in a lot of vector capabilities inside the CPU. And most recently inside Skylake, we have 512-bit vector operations inside, right? And over time, the performance has been increased very significantly, starting from the SSC days to the AVX 512 days inside Skylake. So we do have the hardware capabilities in terms of floating point operations you can do here. Okay, so with that, and with the problem we have on CNN, how do we make it efficient, right? How do we get the best out of the hardware is a challenge that software has. Okay, so the way we do this inside software is this: when you think about deep learning, effectively, at the end of the day, it comes down to a lot of matrix operations, right? And these matrices, quite often they're actually it's multidimensional matrices, right? And how do you do these multidimensional matrices well is key to performance here, okay? And in order, so when you have these large matrices doing multiplications here, and underneath it, you have a hardware which has a different sort of features inside. So one is what I mentioned is vector, right? And the other is you have you have multiple cores. Actually, inside one Skylake system, we have more than 56 cores inside. So is it reminded me so when I worked on supercomputer at that time, like more than 100 nodes, it was considered a big supercomputer. So right now, a single system, you have like 56 cores inside, right? So it's a mini supercomputer inside, really. And so one is how do you do vectorization right? Second way is how do you do parallelization right? Now, another thing which is very important but may not be very intuitive is data locality. Because you want to make sure whenever you bring the data, you actually work on it as many times as possible instead of going to memory all the time, right? So if you do these three things right, then you will get great performance. Okay? So the way we do this is because eventually it's a major operation, so we designed a library specifically for deep learning. This is something what we call math kernel library for deep neural networks. Okay? So Intel has been in the supercomputer business for many years, and so over time we developed a lot of software capabilities for high performance computing, and the math was very important there, right? A lot of matrix operations and that. So we leveraged that and we expanded to include deep learning operations like convolution and so on. So deep MKLDNN is the one it's actually open source. For those of you who are interested, want to know what's going on there, it's actually available. So inside MKLDNN, how we optimize these things to make sure that it is actually very efficient. So we actually do the traditional things people used to do for supercomputers, right? So you want to vectorize it, you want to parallelize it, and quite often you want to do blocking. And the reason you want to do blocking is once you have so you may have a huge matrix, multi-dimensional huge matrix. You don't want to traverse these huge matrices, one by one, because whenever you traverse it, you got out of your cache. Right? You no longer have the reuse here. So you want to block in such a way, you want to do one block at a time, and hopefully that block stays inside your cache. So whenever you access that small block, it is all local, right? So these techniques are going to be very useful here, blocking as well as what we call operator fusion, which is very similar to loop fusion, if you guys did that stuff before in the compiler days. Shilong Manager used to do compilers. In the compiler, we used to do all of these things, loop fusion, loop blocking, in terms of at the compiler loop level. But here is very similar. You do it in the operation level. You do fusion. It's a very similar idea. Okay, so that's how we do this using MKL DNN. All right. Now, the other thing people have been doing is try to go down to lower precision. Because deep learning is very interesting because it's statistical, right? Because that's another thing I should remind me the difference between this and the supercomputer. Supercomputer, you have to be precise in terms of your floating point models and all that. Here, you could play loose actually. So far, it is still FP32, single precision for the most part is good enough, but people want to go down, right? So can you do integer 8? You use 8-bit instead of 32-bit. Once you get to 8-bit, you get a lot of benefits, right? You can get lower memory bandwidth requirement because you don't have a lot of data to move around, and then you actually can compute, you can do it faster as well. So we have invested in integer 8 inside the hardware. In Skylake, we have integer 8 already. But Cascade Lake is where we actually have the full int 8 implementation. That's what we call DL Boost. Okay? So if you look at the performance gain from the Skylake launch at that time, with the optimizations I mentioned earlier, and plus the 2x, you can get to 11x gain if you compare Skylake launch versus Cascade Lake launch. Now the second example I want to show you here is RNN, recurrent neural network, which is different from the CNN was mainly designed for image processing kind of thing, and RNN is more for the language side of things, natural language processing, speech recognition, and so on. Now that looks different. If you even look at the block level, it's no longer that easily parallelizable because it has more of these dependencies horizontally as well as vertically, right? So I do want to understand the same pie chart here. So if you look at this is the MXNet doing something called GNMT, which is the Google Neural Machine Translation Model. A lot of people have been looking at that. And if you look, similarly, if you look at the operations here, the matrix multiply operations is less than half of it. Okay, so you have another half, which is a whole bunch of other stuff, right? So it's no longer as matrix intensive as CNN. Okay, so you may need there are different ways of doing this to make it efficient on your machine here. Okay, so again, if we look at the op intensity, if you remember on the CNN side, these bars are very high. That means you have a lot of operations. Here, the sort of the frequency of these operations is also much lower than before, right? And now intuitively, what you can imagine here is if I compare the operations per data access between the CNN and RNN side, this is this original CNN. We're talking about from 10 to 1,000. There's a lot of reuse here. Here you have very low reuse, right? So that means the job is much harder. Is very different. When you bring in data, the amount of operations you do on top of the data is much less than the CNN side. Okay. Now, as I mentioned earlier, so this is the CNN layers. So you go from you have these are different words here, and then you go from these layers here, right? So because the amount of compute for each node is not as high as before, it is much harder to get the most out of it, right? So if you think about cache data locality, the amount of reuse here is small, so the locality by definition is small. And in order to get the best locality, what you want is to get what we call inter-operation cache locality, right? So from here to the other places, if they happen to be using the same data, then you win because it's no longer going to memory, right? Now, this is much harder to manage because at the programming level, these are from different places, they're from different operations. So it's much harder to statically get the best data locality across different operations. Now, luckily, for CPU, we have a large cache. So cache, by its nature, is dynamic, right? So the data inside cache, you don't care where the data come from. As long as you happen to hit it, that's all you need, right? So if you have one operation here, one operation here, they happen to reuse the same thing, you don't need to explicitly tell the program, please use the same thing because they all happen to be inside cache anyway. So that's the advantage of having a strong memory hierarchy with large cache sizes, and that can actually capture the amount of data you have. So if you look at the GNMT, the matrix size, looks like the weight matrix is 4 meg, the other is like a multiple case, and our cache size is like 14 meg. It's more than enough to hold all the data you have inside this topology here. Okay. Now, another example is the recommendation systems. As I mentioned earlier, this in Facebook, this is the most popular one they have, the widely used one they have, which is also true for other CSPs. When you look at that model, it is also no longer just CNN alone. It actually is a combination of CNN and the other sort of classical machine learning like MLP. So it is and the amount of data usually is very large. So on the CPU side, we actually have a large amount of memory, so memory space and memory as well. So it is an advantage on the CPU side to be able to run these things very efficiently. Okay, so let me look at the training side. Now, recently, that was early last month, early December, there's a new benchmark just created for machine learning called MLPerf. And so that was, I mentioned earlier, there's a Stanford down bench, and then after that, they decide not to do this anymore. They want more of an industrial consortium to come up with a set of standard benchmarks for machine learning. So this is sort of the follow-on to Stanford down bench. And many companies are involved in this for the MLPerf benchmarking activity design, both in terms of defining the benchmarks as well as contributing the benchmarks and participating in the submission. So the first submission for MLPerf happened last month, and Intel was one of the 3 companies actually did this. Okay? So the first round of MLPerf was for training, and they have a few benchmarks. You get to decide what kind of benchmarks you want to submit results for. We submitted 3 results here, 3 benchmark results here. So what you can see here is ResNet 50 NCF and the Minigo. Okay, so NCF is a recommendation system. ResNet 50 is what I mentioned earlier. It's a CNN image recognition kind of thing, and Minigo is plain Go, which is reinforcement learning. Okay, so in all these cases, CPU actually looks, in my mind, pretty reasonable, right? Because the score means compared to the baseline GPU. Okay, so there's a reference GPU implementation for all the benchmarks. And what we have done here is CPU here is close enough. It's 85% of the GPU performance on CNN, on ResNet 50 here. And on NCF, we're actually 60% better than the underlying GPU. Now, this is not the fastest GPU, but it is a volume GPU they have out there. I don't know how many of you are using GPU here. It's NVIDIA P100 they're using here. It's not the V100. But it is still looking pretty good. I mean, 60% better, because for people who are using if customers are happy with the current GPU like this, they should be happy with the CPU also, right? And then for Minigo, we're actually more than 6 times better than the underlying GPU here. So this shows sometimes, when you compare between CPU and GPU, quite often people ask me more than just GPU question, but people ask me, is CPU going to be faster than accelerator, right? And I thought that was a very odd question, because accelerator by definition should be faster than general purpose CPU. If it's not faster, what's the point of doing accelerator, right? So by definition, it should be faster. The question really is how much faster you are, right? If you are 100x faster, then then there's a reason for people to do it. If you're only 2x faster, that's a different story, right? But from the CPU perspective, the question really is how much faster or slower. The question really is, can CPU be solving the problems you have? And for a lot of customers, they already have CPUs. And if they can use whatever you have, you don't have to pay extra. It's like my example at the very beginning. If my team could use a CPU, we didn't have to buy a GPU for this, right? We didn't have to buy an accelerator for this. But for certain people, they may want to have the fastest one. Maybe some of you here, you want to write the paper with the fastest performance. You may want to get an accelerator, and Intel is doing both. Is doing both, general purpose CPU as well as special purpose accelerators here. So these numbers look very respectable. Actually, this is a Forbes article also mentioned our results. They say it's respectable numbers here, and with this kind of performance, we're actually able to provide that kind of capability to real users, right? So this is example from Novartis, which is a drug company in Switzerland. They actually use our Xeon to do training, and they managed to reduce the amount of training time from 11 hours to 30 minutes, right? And that's using 8 CPU nodes here. So it is doable. It's no longer days or weeks, right? You can actually get the work done within, in hours, right? And in this case, it's less than an hour, but quite often maybe in a few hours or a certain number of hours, right? So the key for training is because it has large amount of computation, you want to use a lot of nodes for doing this. And so the key to this is how do you do distributed computing in the efficient way, right? Can you scale out? Because you may have a data center here with tens of nodes, hundreds of nodes, thousands of nodes. Can you actually use all of these CPU nodes to get the training done? And there's a difference between training and inference, because inference is a real time, right? You want have, if you have a business, you have inference on all the time. But for training, you don't do it every day, right? So it could be off, could be, you could do this when your systems are available. You may have a data center, like in the Facebook. Actually, Facebook use their data center to run training as well. And the way to do this is, if Facebook has a big cluster serving the U.S. market, and when during the evening everybody go to sleep, and then all of a sudden these systems become available. So these are all free cycles to them, right? So you run it on these machines, and all of a sudden you get training done as well. So the scalability is important, depending on how many nodes you want to use here, how many nodes you have available. So in this particular case, we're looking at, let's take this as example here. So we used 128 nodes, and the scaling factor is pretty good. It's 120 out of 128. You're almost getting linear speed up. It's more than 90% speed up efficiency here, right? This is another surprise to me, because when I used to work on the supercomputing side, when you go to a certain number of nodes, performance basically plateaued, right? You can't go, no matter how many nodes you add, you just, same performance anyway. But here it seems to be scaling very nicely. Now, I'm from the Bay Area. We work with other universities in the Bay Area also. So UC Berkeley, they actually took our optimized software, in this case Intel Cafe, and they managed to use a supercomputing center in Texas Austin, UT Austin, and they used more than 1,600 CPU nodes. So this shows you how well you can scale, right? If you're really lucky to have a supercomputing center, you can go all the way to 1,600 nodes, and the ResNet 50 you can get it down, in half an hour, right? So it is possible. Oops. Okay. So now let's look at how, as similarly on the inference side, we use different techniques to get inference performance up. On the training side, we also used quite a few sort of techniques to get the training performance up, and mainly on the distributed computing side. So this remind me again, you have a parallel computer, right? This really is a parallel computer here, right? How do you make sure your parallelization is efficient, right? So there are different ways of doing this thing here. One is you want to have an effective way of doing communication specific for machine learning and deep learning. So we actually developed a communications library called MLSL, machine learning scaling library, specifically designed for deep learning, and that's actually built on top of MPI, which is a very popular message passing interface on the high performance computing side. Okay, and you want to increase your scaling efficiency, as well as you want to support different kinds of training algorithms here. So let me get to a little bit more detail here. Okay, so the way to parallelize it is because we're doing mini batch, right? You're doing multiple things, let's say multiple images in the batch, in the mini batch at the same time, and you want to parallelize within the mini batch. That's the easiest way of doing this, because you have data parallelism. You have a lot of data. You want to do things in parallel, right? People also do model parallelism, which means you want to do a portion of model on one node, another portion on the other node. That's much harder to do. And the data parallelism is more scalable. Well, as long as you have your batch size to be larger, you can scale this. And the way to do parallelization here is when you do training, you have two passes. So the way you think about the neural networks is when you go fast. This is forward pass. So let's say take an image. You want this neural network to tell you what this image is. Let's say it's a dog or cat or whatever, right? So the neural network will go down to the end. It will tell you this is a cat, but the ground truth is this probably is a dog, right? So the current network is not good enough, and the way it works is you want to somehow fix the network somehow, right? So the way learning happens is at the end you compare dog and the cat. You want to say, hey, how can I change my neural network to make sure I give the right answer instead of the wrong answer? So you fix your network backwards because you know the answer at the end. So you fix the last layer and then you back propagate to the beginning. So that's how you train your neural networks here, right? So you have two passes here. You have forward pass and you have backward pass. So the training mainly happen in the backward pass. Okay? And within the backward pass, you have a lot of communication going on. So the key part here is, can you make sure these communications are happening efficiently? You do need to communicate, but you want to overlap your computation and the communication at the same time, and therefore you can hide your communication cost, right? Because you have to do work anyway, let the communication happen at the same time, then you're not really bottlenecked by the communications here. So this is the idea we have for the library here. And then you want to increase your efficiency, right? Intuitively, because we're doing data parallelism, the more data you have, the more you can parallelize, right? You can, if you want to go to thousands of nodes, if your data set is tiny, is not much to split, right? But if your data set is big, then you can actually parallelize more easily, right? Now, initially, these algorithms are not really very friendly to large batch size. Once you increase your mini batch size, all of a sudden these algorithms don't work anymore. They don't converge anymore, right? You don't want that to happen. You don't want that to happen either. You want to have a correct result as well as performance. So in the industry, actually, about a year ago, there's a new breakthrough coming from different research groups. So Facebook came up with a way of doing changing learning rate. So that allows you to go to batch size of a few hundreds and so on. Okay, and then Berkeley came up with a new idea to fix the learning rate, and with that you can actually scale as big as like 32,000 in terms of batch size, right? So that's why they can actually go all the way to 1,600 nodes, because they're able to go very far, okay? In terms of large batch size. And then sometimes even that is not sufficient. You want to go even further, even want to go even larger batch size. And how do you? Because once you go large number of nodes, the synchronization cost is going to be more expensive, right? Because imagine if you have 2 people, you can communicate more efficiently. 10 people is much better. And if you go to like 10,000 people, if you want to communicate, synchronize in some way, it is much harder to do. And the cost is going to be higher and higher the more nodes you're going to add here. So Stanford, we actually worked with them very closely. They came up with some research idea to break that bottleneck in terms of synchronization among a lot of nodes here. The idea is very interesting because it also explores the fact that machine learning, particularly deep learning itself, is a stochastic, right? It's not really deterministic. So you can actually try to leverage that fact. You change the algorithm. I don't have to be faithfully executing the exact same thing here. I can actually try to do asynchronous communication, right? Maybe the original algorithm says at the end of the particular phase, all of us have to sync, right? But we decide not to do this. We decide to break all of us into multiple groups. Maybe we only have 10 groups, and all of a sudden we have a factor of 10 here, right? Each group has to synchronize at the end of the one pass, right? So by doing this, your synchronization costs get reduced very significantly. But you also change the algorithm a little bit, really, right? Because you no longer have fully synchronized version. But luckily, because it's deep learning, you can get away with it, and they can still get to the same accuracy by doing this. So that's the basic idea behind what Stanford has done. And with this, we're also getting very good results. So it's a large number of, they got as far as like 9,000 nodes on the weather forecast application here, okay? By working with another national labs here. All right, so that's the end of my presentation. So what we have done here is CPU can actually do the job for deep learning, right? And it has been, the performance has been improved very significantly in the past 2-3 years, more than 200x even on the software optimizations alone. And with the number of nodes, we can scale out to thousands of nodes when you do training. So we can do really well on both inference, deep learning inference, and deep learning training side. And there are a lot of customers using this already. I think this is really giving people an alternative, a different option. If you don't want to invest in accelerators, you can do this. But obviously, if you want to buy accelerator, that's your choice as well, right? So we have a variety of compute capabilities that users can do here. If you're interested in playing with the software, as you can see, the key to this is software, optimized software. And you can get it from the Intel website, which has the information there. And in many of these cases, we have actually upstreamed our change to the main the software branches here. For example, TensorFlow, we upstream to the Google site. For PyTorch, we upstream to the PyTorch site as well. And you can download from there as well. Go to TensorFlow. There's a Intel optimized binary listed on the TensorFlow site. On the MXNet as well as PyTorch side, we actually part of the default build for them. TensorFlow is not quite there yet, and TensorFlow you actually have to explicitly look for the Intel optimized version in terms of the binary. So these things are all available, and a lot of these actually all of these are open source. If you want to understand the underlying implementation techniques we've been using, MKLDNN is the key to all of these, and it's open source. And each framework, we do additional optimizations inside, and these are also open source, so they're all available. Okay. All right, and we have a team here in Haifa, and if you cannot find me, you can always find them locally. So, any questions? Yes.
I have several questions.
Okay.
Let me start from the first one.
Okay.
The architecture of the computers you are using, you had a diagram, squares and fields coming out, and connection coming out. Now, what is the communication between the processors? Is it always through the memory, or there is direct communication from processor to its neighbor?
Yeah. Okay. So the question is communication. Is that
Let's see the diagram.
okay? All right. So there are two levels here. So I wasn't sure which diagram you're looking for here.
You passed it.
I passed it already. Okay.
With squares and no, not this one. I don't see it. Maybe you didn't pass it.
Okay. Let me know which one you are looking for here.
Oh,
Not this one, right? Not this one.
this one.
This one?
This one. Is this the
No, this is not the diagram for the computer. This is the diagram for the. Okay, so maybe what you. Let me see. Okay, so there's a diagram here. Okay, so let's see. Okay, so there are two levels here. One level is there's a diagram here on the single node. There's a difference between single node and the multiple nodes. Okay, so when you
the communication
yeah.
between a node and its other node.
Yeah, so the communication between nodes, between one node and the another node, depends on how you have, what kind of interconnect you have. So the assumption we are making here is you just have a very regular interconnect, like Ethernet. Okay, you have Ethernet. You have all these computers connected on the Ethernet. Now Intel does provide a special network called OPA, but that's not our assumption here. Our assumption is because majority of people, if you go to a cloud service provider, they just have Ethernet over there, whatever cable they have there. So we don't make any special assumptions there. And the software layer we have is the message passing. So it's not going through memory. It's not shared memory between nodes. It's actually message passing. I sent you, it's message passing.
You send message from a processor to a processor?
Yes, yes.
I see. So it's asynchronous.
It's,
Not synchronous.
it's,
The processor are not synchronous.
the process is not synchronous. Yeah, that's right. So I just sent you a message. So I have a bunch of data. Yeah, I have a bunch of data. I just sent you a data, right? So quite often they have either one-to-one kind of message, and quite often they have this all reduce, which means if 10 of us are working on something together, we all need to synchronize, get the same kind of data synchronized, and then distribute it back to everyone also.
And what is the structure of the memory? There is a local memory, cache. What? I don't have
I'll repeat his question, but I do think we want other people have a chance to ask questions also. So your follow-up question is, what is the
structure of the memory?
what is structure? There's no difference. It's just the usual memory we have on the CPU. There's nothing special here. It's just a regular CPU with regular memory, a regular cache hierarchy, and between CPUs we do message passing to communicate. Okay. Yes, you have a question. Yes. Yes. Oh, good. Yes. 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 Do you work for Intel? Or? so that's a question we actually, I run a software team. Whenever I talk to the hardware people, they ask me that question. They say, "Oh, you're doing great. It's fine. I'm very happy you got more than 200x. But how have you left any transistor behind? Have you, utilized all the capabilities I give you, right?" So the answer is depends. For certain applications, we have hit the what we call roof line. So actually, Renat's team, her team, she's part of my org, but her team is chartered to get to the roof line. So she will go in and say, with the particular algorithm here, with all the hardware capabilities here, what is the fundamental limitation for performance here, right? Because if you only can do 2 operations per second, I cannot expect you to do more than 2, right? So that's the level of roof line her team is coming up with. And then I have another team that is actually doing these optimizations inside these frameworks. And so that becomes their goal, to get to the roof line. And we do use that as a metric to compare how far away we are. And for quite a few of these, we hit the roof line already. But not everything's at the roof line yet. Part of this is also roof line is very time-consuming to get to. You can imagine, given a topology, what is the best you can do? It's not like for certain topologies we are there already. Yeah, like a Resonate 50 what I show you, Resonate 50, that particular topology for that particular framework, we have hit the roof line. But we also have other frameworks we're not quite there yet. Now this is the setup. Now the spec. If you're almost at the roof, yeah. Then what's the logic behind having accelerators? The computer cells are heavy. Change the complete structure so that the roof kind of moves. Yeah. So exactly. So you have accelerator, your roof line would change, right? because the CPU we're using is designed for running all kinds of workloads. It's not designed for specifically for deep learning, right? So if you customize your hardware for deep learning alone, you can potentially eliminate some of these quote unquote overhead because it's a general purpose machine, right? So you can do things more efficiently if the only thing you do is for major operation, right? It's both. So the deep learning workloads, to do it well, quite often you need a amount of compute units, right? So ALU, you need the peak flops. That's what we need. That's one thing you need, and the other is memory bandwidth, right? So if you cannot, as I mentioned earlier, if you cannot do the locality thing well for certain things you cannot do well, having a lot of bandwidth will certainly help you, right? So and then can you have large amount of memory that can help you also. But then it comes down to how expensive this thing will become, and so the other things will kick in as well. You can't, whatever you ask, there's a cost for this, right? And the more narrow you go with a particular workload, when things change a little bit, you're no longer matching that anymore, right? So for example, the reason we do very well on the CPU side for some of these workloads is if you do a straightforward matrix operation, you don't have any branch. If you don't do well on branch, maybe it's okay for simple matrix operation. But if your code starts to have branches inside all these things, then all of a sudden, you're on a machine that don't support these things well anymore. So now the thing about accelerator really is, it's not about functionality, because accelerator has a CPU as the backup, right? If you cannot do well on accelerator, you can always go back to CPU. Now the only difference is just a cost for you. If you go back, it's a long way to go back. Okay, thank you.
Thank you.